Alright, so hello everyone today. So we're going to cover section 5.3, combining functions. So combining functions arithmetically and composing functions. There is a section 5.2, but it doesn't have a lot of relevant information, so we skip it. So if you think you skipped a lecture, 5.2 we don't cover as of now. Alright, so addition, subtraction, and multiplication of functions. So we let f and g be two functions. We define the sum of f plus g and the difference f minus g, and the product as f times g as follows. So we just assume it's multiplied if they're written next to each other. F plus g of x equals f of x plus g of x, f minus g of x equals f of x minus g of x, and f times g of x equals f of x times g of x. For all these functions, the domain is everything that is in both the domain and of f and the domain of g. So basically, what you do is you have your domain. So let's say we have the domain of f. What is domain of g? And we intersect them to make sure that we have elements from both. So that's an intersection of those two domains. So if something can't be included for g, we can't put it in for the entire function plus g. So we let f and g be two functions. We define the quotient as f divided by g as follows. F divided by g of x is f of x divided by g of x. The domain of the quotient is not just everything that is in both the domain of f and the domain of g. If g of x equals 0, the denominator, then we try to when we try to compute f divided by g of x, we divide by 0. So we also need to exclude all the values where g of x is equal to 0. So that's the additional. Not only do we need the intersections of the domains, we need to exclude any points where the denominator is 0 as well, because we introduce new restrictions to the domain. So this is just a simple, they define as f of 3, for our first exercise, they say let f of 3 equal 2 and g of 3 equal -1, and they just want us to find the following. So it's easiest just to rewrite these in the long form notation. So if we have our first example of f plus g of 3, we write it as f of 3 plus g of 3. So f of 3 is 2, and we're going to add that to g of 3, which is -1. And we're going to get 1 back out. Same thing with subtraction. So f minus g of 3, we get f of 3 minus g of 3, whoops, just minus g of 3. And that's going to equal, and it's always good to put things in parentheses when you're subtracting them. So we're going to have 2 minus a -1, which will give us 2 plus 1, which is 3. Next, we're going to have f times g of 3, so that's f of 3 times g of 3, which is going to be 2 times -1. Once again, good idea to put parentheses in there anyway. If I have parentheses in there, I don't need the multiplication symbol or the dot, and so that's going to give us -2 back out for that. And then we have this last one where we have f divided by g of 3. So we're going to have f of 3 divided by g of 3. And here that's going to give us 2 over -1, which will give us, is f of 3 is 2, and g of 3 is -1. That gives us -2 back out. The only reason why we get the same answer for both of these is multiplying and dividing by -1 gives you the same number. Next, it wants us to take these, in the second exercise, it wants us to let f of x equal x squared minus 1 and g of x to equal x minus 5, and we want to determine the domain and the range for those. So here we're subtracting. So we're going to say that we have f of x minus g of x. So that's going to be x squared minus 1. Good idea to put these in parentheses, minus and it's required here, minus my g of x, which was x minus 5. So I just made those substitutions for f of x and g of x. And now I'm just going to carry out the distributing the negative. And so I'm going to have x squared minus 1. That was my f of x. And I distribute the negative across my g of x, which was x now becomes negative x plus 5. And then I have two terms I can combine, so that'll be x squared. And we're going to say minus x, and then that's going to be negative 1 and 5, gives us positive 4. And that's my final answer right there. The domain, well, the domain for this is all real numbers. Double bar R. Domain for G, since it's linear, is all real numbers. Now, I intersect all real numbers with all real numbers, and I'm going to get all real numbers back out. Plus, you can see this is a polynomial, and we talked about that earlier, how a polynomial has the domain of all real numbers. I can plug in any value for x. All right, so let me change colors for this. And so now we have g over f of x, so that's g of x divided by f of x. So that's going to give us x minus 5 over x squared minus 1. There's no way I can simplify this. There are no factors that x minus 5 will cancel with in the denominator, so that's it. But the domain is going to be all real numbers, except now x squared minus 1 can't equal 0. Well, when does that happen? Well, x squared minus 1 equals 0 exactly when x squared equals 1 or x equals plus or minus 1. I took the square root of both sides. Remember when you're solving for an unknown, that's when you get the plus or minus. So I have to say when that happens, and that happens exactly when x is equal to negative 1 or 1. And if we had to write this in interval notation, well, we'd say we want all the numbers from negative infinity to negative 1, not including negative 1, negative 1 to 1. Remember, there's an infinite number of numbers between any two numbers. And the union 1 to positive infinity. So see how I skipped exactly the points I didn't want. I skipped the negative 1, and I skipped the 1, so those are no longer. So I had to be careful since I was dividing. Whatever would give 0 in my denominator, I had to exclude that from my domain. So my domain, all real numbers in my original two functions. When I divided, anything that gave me 0 had to be a new restriction in my domain. Composing functions. So we let f and g be two functions where we define the composition as f, this open circle g, as follows. F open circle g of x equals f of g of x. And then we read this as f composed with g or f of g. Usually just say f of g. This means we put x into our rule for g of x, and then we put the answer we get in there to our rule for f of x. Note this is not multiplication. The notation looks similar, but the circle is larger and empty. So here we have the following. We let f equal just a set of points. So in other words, this is a finite number of things that are defined by f. It's not an actual function where we get x. So if it says we plug in 3, we get 15 back out. We plug in 2, we get a negative 1 back out. And if we plug in negative 1, we get 1 back out. And we let g of x actually be a function of x squared minus 7. So we want to compute the following. So first it says, so I'm going to rewrite this as f composed with g composed with f of negative 1 as g of f of negative 1. So what's f? Well, negative 1 gets paired with 1. So I'm going to replace this negative 1 right here, this f of negative 1. I'm going to replace that with 1 because that's where negative 1 gets mapped to. So that's going to be g of 1. Well, what's g? Well, that takes a number, 1 in this case, squares it, and subtracts 7 from it. So 1 squared is 1 minus 7 is negative 6. So that's my answer for that one. F composed with g of 3. We write that as f of g of 3. So we have to plug it into the function first this time and see what we get back out. So I'm going to say f of, and this, now we're going to have g of 3. So plug in 3 for my x squared. So I'm going to have 3 quantity squared minus 7. So that's going to give us an f of, and here we have 9 minus 7. And so that gives us an f of 2. We go up here, 2 went to -1, so that's going to be -1 back out. Now, some of you are thinking, like, what if I got a number that wasn't in this set? Like, let's say I got 17 back out. Well, if it's not something that, like, 3 gets mapped to 15, 2 gets mapped to -1, and -1 gets mapped to 1. If it's not in this list, then it just doesn't exist, and you probably did your math incorrectly. So double check your math, or you might have reversed the composition or something like that. Here we have something kind of silly where we compose a function with itself, which you can do. So f of 2. And so f of 2, well, where does 2 go? It goes to -1, so it'll be f of -1. And where does -1 go? It goes to 1. So that would just be 1 back out. So you can compose a function with itself. That totally can happen. So now for our fourth exercise and composition. It wants us to find the value. So we have our f of x equal x squared minus 1 and our g of x equal 2x minus 1. So it wants us to find the value of g of f of 2. So once again, two ways you can do this. You can find the formula and plug it in, or you can plug it in as you go like we were doing before. So we say g of f of 2. So what does f do? F squares a number and subtracts 1 from it. So I'm going to say this is equal to g of, and it's going to square that 2. It's going to subtract 1 from it. So I replace the function f of 2, or I replace the f of 2 with 2 squared minus 1, which would give us g of 2 squared is 4 minus 1 is 3. So g of 3. Well, what does g do? It doubles it and subtracts 1. So I'm going to say 2 times 3 minus 1. This is going to be 6 minus 1, which is 5. So our answer for that is 5. Next it says find and simplify the formula for f of g of x. So in order to do that, I'm going to rewrite that as f for part B, f of g of x. And so now I'm going to say that's going to be, well, what's g of x? G of x, I'm going to say f of g of x, and g of x was 2x minus 1. And that equals, and now I'm going to have what? F of 2x. So now I'm going to write this 2x minus 1. That's going to be what I plug in for x now. So I'm going to say 2x minus 1 quantity squared minus 1. And so I replaced the x in my f of x, and I plugged in right here, I plugged in my 2x minus 1. And so that became 2x minus 1. And I plug in it here, so it's squared minus 1. So I got to FOIL that out. So you might want to do that on a separate sheet of paper somewhere. I'm just going to do it over here, just so I can keep all my work on one sheet, or the important work. So 2x minus 1 times 2x minus 1. So it's going to be 4x squared, right? 2x times 2x, and then 2x minus 1 times -1 is -2x. -1 times 2x is -2x, and then -1 times -1 is +1. So I'm going to get 4x squared minus 4x plus 1. Well, let's copy that over here. I just want to keep it all on the same sheet of paper for my answers here. I just didn't want to make this jump to 4x squared minus 4x plus 1 without showing you the math of multiplying that out. And then I'm going to subtract 1 off of it. Don't forget this -1 that was here. And so that's going to give us 4x squared minus 4x, and then plus 1 minus 1, and then 1's go away. Next, it says find and simplify formulas for decomposing in the other direction. So now we're going to say g of f of x. And so what is that going to do? Well, we're going to write down our g of, well, what does f do? It takes a number, squares it, and subtracts 1 for it. So I'm going to have x squared minus 1 in here. Then I plug that in for g. So I'm going to replace this x right here with x squared minus 1. And when I do that, then I'm going to say, what does g do? It doubles something. So my something that I'm doubling is going to be x squared minus 1, my f of x essentially. And then it subtracts 1 from it. So when I do that, I'm going to get the 2 multiplied through, which is going to give me 2x squared minus 2, and then minus 1, which gives me 2x squared minus 3. So looking at this, we can see that these values are drastically different. So the order of composition matters. I can't just say f composed with g is the same thing as g composed with f. That doesn't happen. The only kind of type it happens is, if you have trivial functions, or you're composing them as inverses. We'll talk more about that in the next section. So you can see the order of composition matters. Here's another way of looking at composition is on a graph. So we have my function, my orange line, which is my f. I'm going to have my purple line here, be my g. I've been using orange and purple a lot. One, because they contrast each other well, and two, because they're markers that work. All my other markers are running out. So first it wants multiplication. So it's going to say f times g. So f of 3 times g of 3 is what we want here. So I'm going to go look and say, okay, what's f of 3? So if I look at 3 on the x-axis, f of 3, so 3 comma, and actually I should do this in orange since I'm talking about my f function here. So if I plug in 3, I get 1 back out. All right, so my f part here becomes 1 times, and my g, if I look up 3 on my x-axis for my g function, well, that's down here at -5. So that's the point 3, -5. So when I plug in 3, I get -5 back out. So it's going to be multiplied times -5, which gives me -5 back out. Now compositions are a little bit different because you kind of have to go on a chase. Because here we have f composed with g of -1. So I have f of g of -1. So what is that going to give us? Well, I first have to find out what g of -1 is. So I go over here and I plug in -1 and I get -1 comma 3 back out. So that means when I plug in 3, I'm going to have f of 3. Right? So when I plug in -1 into g, I get 3 back out. So that becomes f of 3. So once again, f of 3. If I look up 3 on my x-axis, I get 1 back out. This gives me 1. So it's kind of like you have to chase this. First point, you get plug in -1, you get 3 back out. You plug in 3, you get 1 back out into my two separate functions. I suggest students practice this a lot. It shows up on tests. It shows up on finals. And it's a very, because all you have to do is basically just follow the graph. You don't have to do any actual multiplication or addition besides just the individual process of either plugging in or multiplying. A lot of students miss this. They don't know how to read the graph, and that really hinders them. So practice those problems. So the domain of composition, the domain of f composed with g is a little bit more complicated. We need x to be in the domain of g so that g is defined. Then we need the output g of x to be in the domain of f. For example, we let f of x equal the square root of x and g of x equal x plus 7. If we evaluate f of g of -3, we first find that g of -3 is equal to 4. So it's going to be -3 plus 7 is 4. Then we evaluate f of 4 as 2. Even though -3 is not in the domain of f, it is in the domain of f composed with g. So basically, you're going to have these circles, right? So these are going to be your domains where you start. So f goes to this, goes to g, and then so we're going to have g right here, and then that's going to be, well, x goes to g of x when we're composing in this direction, and then g of x goes to f composed with g of x. So this is my function g, and this is my function f. Notice f comes first here, but when you compose them, it's in the reverse direction as you go. And then f composed with g skips from the domain that would have been g all the way to f. So that's f composed with g. So basically, you're looking at the domain of g that satisfies everything for your composition. So it says it wants us to find in exercise 6, it lets f of x be x minus 4 and g of x to be the square root of x. So it wants us to find f composed with g of 9. So once again, this is easiest to work in parts. So we say f composed with g of 9. What does g do? G takes the square root of a number. So this is going to be f of the square root of 9. And what does f do? Well, it's going to be f of 3. Well, it takes a number, subtracts 4 from it. So it's going to be 3 minus 4, which is negative 1. And it says give the formula, and for the second part it says give the formula and domain for G composed with F. So here we have G of F of X. So what is X? So I'm going to plug in, I'm going to say G of, well, what is F of X? It's X minus 4. And what does G do? It takes the square root of whatever you plug in. So the square root of X minus 4. So we don't need to do in simplifying. And now it wants us to find the domain. See, originally I couldn't plug in negative numbers into X. But here I'm allowed to do that because I was able to plug in anything for F, right? But remember, F moves everything 4 units to the right. So things that I couldn't plug in, like I can't plug in 3 anymore, where I could plug in 3 here. But I can't do it here because that'll give me negative 1 underneath my radical. So basically we want the domain to be where we have x minus 4 greater than or equal to 0. Well, that happens when x is greater than or equal to 4. So our domain is going to be all the numbers that are greater than 4, including 4. So it's going to be 4 all the way to positive infinity. So that's our new domain. So the domain for the original G of X was from 0 to infinity, and for F it was all real numbers. But since this function moved everything to the right 4 units, I had to move the domain right 4 units. So in this case, it went from 4 to infinity. All right, so that's it for today. You all have a great one.